Hey everybody, in this video we're going to talk about relationships involving delta H for chemical reactions. So to start this video off, suppose we have this chemical equation down here which describes the formation of water from hydrogen gas and ozone. And we want to know its delta H value, but suppose that we cannot actually carry this chemical reaction out in our laboratory. And there's a lot of reasons why you may be unable to carry a chemical reaction out. Maybe the reagents are just too expensive, maybe the reaction is too dangerous, maybe you just don't have the proper equipment in your laboratory to carry out such a chemical reaction. But for whatever reason, we can't actually observe this chemical reaction, but let's say we want to know its delta H value. We want to know if it's endothermic or if it's exothermic, and not just that, but how endothermic or how exothermic this reaction is. Well, it turns out we can actually figure out the delta H value for this chemical reaction without running the chemical reaction. We just have to know some other pieces of information. And it turns out that if we know the delta H values for these two reactions that are shown in blue, that can actually help us with the help of these relationships that we're going to talk about in just a little bit. That's actually going to help us to determine delta H for the equation in red without carrying the chemical reaction out. And so how do we do that? What are these relationships? So the relationships have to do with when you manipulate chemical equations. So when you multiply a chemical equation by a factor, how does that affect delta H? When you reverse a chemical equation in which products become reactants, reactants become products, how does that affect delta H? And that's what we're going to talk about. So the first relationship has to do with when you multiply an equation by a factor. If you multiply a chemical equation by a factor, then the resulting delta H value for that new equation is simply going to be the old delta H multiplied by that same factor. So suppose we have this chemical reaction here where we have A plus 2B yields C, and let's say that the delta H value for this, let's just call it delta H1. Now suppose we take this equation and multiply it by a factor of 3. Well, that's going to give us 3A plus 6B yields 3C. And we're going to call the delta H for this new reaction delta H2. So according to this rule, according to this relationship, if we want to know delta H2 and we already know delta H1, all we have to do is take that factor that we multiplied the first equation by, which is 3 in this case, 3 times delta H1, and that'll give us delta H2. So again, if you multiply an equation by a factor, you got to multiply delta H by that same factor to get that new delta H value for that new equation. The second relationship, excuse me, the second relationship has to do with when you reverse a chemical equation. So products become reactants, reactants become products. If you reverse a chemical equation, then the sign of delta H must change. So suppose I have that same equation as in the previous slide, A plus 2B yields C, and let's say that its delta H value, we're just going to call it delta H1 again. And let's say that we reverse this equation, well that's going to give us C yields A plus 2B. If I want to know the delta H for this equation, which I'll call delta H2, then I'm simply going to reverse the sign of delta H1. So to get delta H2, it's simply going to be the negative or the opposite of that first delta H value. Then there's relationship number 3, which has to do with when you add chemical equations together. When you add two or more chemical equations together, how does that affect a delta H value? So the relationship goes as follows. If you have a chemical equation that can be expressed as the sum of a series of steps, so if you have an equation that can be represented as a sum of other chemical equations, then that means that the resulting delta H value for that summation, for that new equation, is going to be the sum of the heats of reaction, so the sum of the delta H values for each of those individual steps. And this relationship has a common name. It's called Hess's law. So it's Hess's law. So just to demonstrate this relationship, let's say we have A plus 2B yields C with a delta H value of delta H1, and then we have another chemical equation which is C yields 2D with a delta H value of delta H2. And so let's say we add these two equations together. If we add these two equations together, then those C's are going to cancel out because there's one on the right, one on the left, so those are going to cancel out, and the resulting equation would read A plus 2B yields 2D. And if I want to know the delta H for this new equation, which I'll call delta H3, then all I have to do is simply add together delta H's for the first and second chemical reactions. So again, if you have a chemical equation that can be expressed as a sum of other chemical equations, to get the delta H value for the summation equation, you're just going to add together the delta H values for those individual equations that added up to give you your sum. So without further ado, let's jump right into a problem. So let me just explain this problem. There really isn't a list of instructions, but let me just explain the instructions real quick. So let's say that we want to figure out delta H for this chemical reaction that is shown in red. So we have 5 carbons plus 6 diatomic hydrogen molecules yields a molecule of C5H12, which is called pentane. So we have carbon and hydrogen making pentane. And we want to know delta H for that reaction. And we don't know it, but we do have the delta H values for these 3 chemical equations that are in black. So that top equation, that's the combustion of pentane. So we have pentane and oxygen reacting to make CO2 and water. And then in the middle, we have the formation of CO2 from carbon and oxygen gas. And then on the equation on the bottom, we have the formation of water from hydrogen and oxygen gas. And all of these delta H values are shown. For the combustion of pentane, it's negative 3,508.8 kilojoules. For the formation of CO2, it's going to be negative 393.5 kilojoules. And then for the formation of water, it's going to be negative 483.5 kilojoules. So the way that we're going to tackle this problem is we are going to manipulate these 3 equations such that when we add them together, we're going to get that equation in red, which I like to call our target equation. So is there any way that we can manipulate these 3 equations such that when we add them together, they'll give us the equation in red? Notice that if we add the 3 equations together right now, that is certainly not going to give us the equation in red. So how can we do that? It's sort of like solving a puzzle, which is why I really enjoy these problems, because I really enjoy solving puzzles. And let's see, where are we going to start off? Well, one thing that is jumping out at me is that in the equation on top, we have pentane, C5H12, on the left, but in our target equation, pentane is on the right. So that must mean that we need to reverse the equation up top. We have to reverse that equation for the combustion of pentane. So I'm going to go ahead and do that. So I've reversed the equation, so now I have pentane and oxygen on the right, and I have CO2 and water on the left. Since I've reversed this equation, I'm going to have to take that delta H value and change its sign. So negative 3,508.8 kilojoules is going to become positive 3,508.8 kilojoules. So now we have pentane on the right side where it belongs. Let's see, what else could we do to get our target equation when we add these 3 equations together? Well, it looks to me like in our target equation we have 5 carbons, and in the equation in the middle here where we have the formation of CO2 from carbon and oxygen, we only have 1 carbon. So it looks like we're going to have to take that equation in the middle and multiply it by a factor of 5. So that's going to give us this new equation where we have 5 carbons, 5 diatomic oxygen molecules, and 5 CO2 molecules. Since we multiplied this middle equation by 5, we also have to multiply its corresponding delta H value by 5. So that minus 393.5 kilojoules, we're going to multiply it by 5, and it's going to become minus 1,967.5 kilojoules. So what else can we do such that when we add these 3 equations together, they're going to give us that equation in red? Do you think we can add them together now, and that's going to give us the equation in red? Well, it doesn't look like it, because it looks to me like we have 6 waters on the left. If we add them all together, we have 2 waters on the right, and the waters need to cancel out with one another, because water does not appear in our target equation. So we have to manipulate the equation. We have to manipulate the equation on the bottom as well. So what are we going to do to that bottom equation so that those waters are going to cancel out. Well, again, we have 6 waters on the left side up here. We have 2 on the right over here. So it looks to me like we're going to need 6 waters on both sides, such that when we add all these 3 things together, those waters will cancel. And so the factor that I need to multiply the bottom equation by is going to be 3. So we take that bottom equation, we multiply it by a factor of 3. That's going to give us 6 hydrogen molecules plus 3 oxygen molecules yields 6 water molecules. And now it looks as if they're going to cancel out when we add everything together. But notice again, since we multiply that equation by a factor of 3, we also have to take that negative 483.5 kilojoules. We got to multiply that by 3 also. So we take that minus 483.5 kilojoules, multiply it by 3. That's going to give us 1,450.5 kilojoules. So let's see. Can we add these 3 equations together to give us our target equation? Well, it looks like the CO2s are going to cancel. We have 5 on the left, we have 5 on the right. It looks like the waters are going to cancel. 6 on the left, 6 on the right. Looks like the oxygens are going to cancel because we have 8 on the right, and then collectively we have 8 on the left, 5 from this equation and 3 from this equation. And so it looks to me like on the left side we have 5 carbons and 6 diatomic hydrogen molecules, and on the right side we have 1 molecule of pentane. So now we're in a position where we can figure out delta H because we've just manipulated the chemical equations such that when we add them together we get the equation that we want. So now all we have to do is just add together these 3 new delta H values that we have, and that's going to give us our delta H value. And so if we add those 3 chemical equations together, we're going to get delta H for this reaction in red is going to be positive 90.8 kilojoules. So again, it's just like solving a puzzle. Got to manipulate those equations through some combination of reversing equations or multiplying them by a factor and then add them together. Make sure you apply those relationships for delta H with every little thing that you do to manipulate each equation, and that'll lead you ultimately to your answer. All right, I hope this video was helpful, and good luck in your future thermodynamic endeavors.